What makes black host rocks so valuable to gemstone discovery is not appearance, but memory. These stones retain the physical record of forces that operated far below the surface, long before erosion exposed anything of interest to human eyes. Heat, pressure, chemical exchange, and fluid movement leave signatures that remain readable millions of years later. When those signatures align, gemstones become possible. In many parts of the United States, gemstone-bearing regions share a common geological ancestry. They formed where ancient continental crust collided, stretched, fractured, or melted. Black rocks are frequent in these environments because iron-rich minerals dominate under extreme conditions. Iron absorbs light, producing darker coloration, but more importantly, it stabilizes crystal structures during growth. Without iron-rich host systems, many gemstones could not grow to size or clarity. One of the most important gemstone-related processes recorded by black rocks is metasomatism. This occurs when mineral-rich fluids move through solid rock, altering its chemistry without fully melting it. These fluids often originate from deep magmatic sources or dehydrating metamorphic rocks. As they move, they carry aluminum, beryllium, chromium, vanadium, and other elements essential for gemstones such as emerald, ruby, sapphire, and tourmaline. Black shale, amphibolite, and altered basalt are common pathways for these fluids. Their fine grain size, fracture density, and chemical makeup allow fluids to circulate efficiently. Over time, this circulation concentrates rare elements into localized zones. When temperature and pressure remain stable long enough, crystals begin to grow, slowly, methodically, and invisibly. Emerald formation provides a clear example. Emerald requires a rare coincidence. Beryllium from granitic sources and chromium, or vanadium from mafic or ultramafic rocks, must meet without destroying each other chemically. Black rocks, such as amphibolite and black shale, often serve as the chromium source, while nearby granitic intrusions supply beryllium. Where these systems intersect, emerald becomes possible. The emerald does not form inside the black rock itself. It forms along the contact zones, fractures, and fluid pathways created by the black rock's presence. This is why emerald districts often show dark, altered host rocks nearby, even if the gem-bearing veins appear lighter in color. Tourmaline follows a similar pattern. It forms in chemically complex environments where boron-rich fluids interact with aluminum-rich rocks. Black schists, slates, and amphibolites often mark these environments. In the United States, tourmaline-bearing regions frequently show dark, metamorphic host rocks cut by pegmatite veins. The pegmatite provides boron and silica, while the black host rock contributes aluminum and structural confinement. Garnet is one of the most reliable indicators linked to black rocks. Unlike many gemstones, garnet forms readily under a wide range of pressures and temperatures, but high-quality garnet requires stability. Amphibolite-grade metamorphism produces ideal conditions. When black basaltic rocks are buried and altered, garnet grows within them as pressure increases. Over time, erosion frees these garnets, concentrating them in streams and soils. This is why garnet-rich gravels often appear downstream from dark, massive bedrock. The garnets survive transport because of their hardness and density, while the host rock breaks down and disappears. Sapphire and ruby share a structural foundation. Corundum. Corundum requires aluminum-rich environments with very low silica content. Black rocks play a critical role here by excluding silica. When aluminum-rich sediments or basalts are metamorphosed without significant silica input, corundum becomes stable. Trace chromium produces ruby, iron and titanium produce sapphire. Many U.S. sapphire deposits are secondary, meaning the gemstones were transported from their original formation site. Black volcanic rocks such as basalt act as carriers, lifting corundum crystals from depth during eruption. The basalt weathers, but the sapphires remain, accumulating in river systems where density sorting concentrates them. This is why gemstone prospectors pay close attention to black sand layers in rivers. These layers are composed of heavy minerals, magnetite, ilmenite, garnet, and often accompany sapphire, zircon, and sometimes diamond indicators. Black sand is not valuable by itself, but it confirms that the river is performing effective density separation. Density is the governing rule of gemstone accumulation. Water does not care about beauty or value. It sorts material by weight and shape. Gemstones survive transport because they are hard and dense. Black host rocks are often the source of those dense minerals, which means they indirectly guide where gemstones settle. Diamond geology is perhaps the most misunderstood of all. Diamonds do not form in black rocks, but black rocks often signal proximity to diamond-bearing systems. Kimberlite, the primary carrier of diamonds, is frequently dark, fine-grained, and easily weathered. When kimberlite erodes, it leaves behind indicator minerals such as garnet, ilmenite, and chromite, many of which appear dark or black. In regions where black ultramafic rocks exist, especially those enriched in chromium and magnesium, the possibility of diamond indicators increases. While diamonds are rare, the geological conditions required to host them are extremely specific. Black rocks help narrow the search by confirming mantle-derived activity. One of the most important lessons for gemstone discovery is that gemstones rarely announce themselves at the surface. They are the final expression of deep systems. The surface clues are indirect. Altered rock color, unusual density, fracture patterns, and mineral associations that appear insignificant to the untrained eye. This is why professional gemstone exploration begins with elimination rather than excitement. Rocks that cannot support gemstone formation are ruled out quickly. Black rocks are rarely ruled out. Instead, they are evaluated for context. Are they associated with faults? Are there signs of fluid movement? Do they occur near intrusive contacts? Has erosion exposed them long enough to release heavy minerals into nearby streams? When these questions align, the ground becomes interesting. In the United States, many productive gemstone areas were discovered accidentally by people who did not understand the geology, but success followed only when patterns were recognized. Modern prospectors benefit from that accumulated knowledge. They know that gemstone systems are not random. They follow structural trends, chemical gradients, and physical laws. Black rocks serve as anchors in this process. They stabilize heat, guide fluids, and preserve evidence. They may not contain gemstones themselves, but without them, gemstone systems would not exist. The most valuable skill in gemstone discovery is patience. Gemstones form slowly, they are released slowly, and they are found slowly. Black rocks encourage that mindset. They force observation rather than impulse. They reward those who look beyond color and shape, focusing instead on structure and history. Every dark stone underfoot represents a question. What happened here? What pressures acted? What fluids moved through? What minerals were present? When those questions are asked consistently, discovery becomes systematic rather than accidental. This approach separates casual rock collecting from serious geological interpretation. It transforms walking into surveying and looking into reading. Pro-gems exist to support that transformation, not by promising shortcuts, but by explaining the rules, not by chasing sparkle, but by understanding structure. Because real value in geology forms quietly, hides patiently, and reveals itself only when the story of the rock is fully understood.